Alrighty, so let us continue our discussion of the Coulomb force, the electric force. Last time we saw that if we have two charges, say Q1 and Q2, and these two charges are separated by a distance r, then the force between these two charges would be given by the Coulomb force. F is 1 over 4 pi epsilon naught Q1, Q2 over r squared. Okay. Now, one thing I tried to make very clear was, of course, charges come in two types, positive and negative. However, when you go to use this equation, usually in a textbook it's written with absolute values around the q's. Also, you might see something like 1 over 4 pi epsilon naught Q1, Q2 over r cubed r hat. Okay? Now, this version seems different than the previous version, obviously, because we have the force is inversely proportional to the cube of the distance rather than the square. However, that's not really true, because technically this unit vector here is kind of canceling one of those r's on the bottom, so it's still r squared. Okay, so if you see this, don't let it confuse you. This is just a way of writing the same exact equation as this one, but in vector form, so you see the direction. This r hat means the force is in the direction of r being the distance from one charge to the other. Okay, I'm not going to write it this way just because I want to avoid that possible confusion. The actual force depends on the square of the distance, not the cube. This is just a mathematical way of writing it so we get all the vector notation stuff in. So don't worry about this. This is the version we're going to use here. And along with this, the whole absolute values thing, I'm probably not going to write the absolute values on this equation anymore, but we're going to follow the rule because it is important. It turns out when you go plug the numbers into this equation, even if the charges are negative, some are positive, some are negative, whatever, you always plug the charges into this equation as positive numbers. Okay, so if Q2 happens to be negative, you don't put the negative charge in for Q2, you put the positive version of it. However, if you do it that way, and you have to get the directions right, that means you, as the physicist, as the person calculating this force, you have to go in and put whether this force is going to be positive or negative. And again, how do we do it? I said, well, let's take the example where Q1 is positive and Q2 is negative. Well, we know the rule says that if the two charges are like charges, that means they're both positive or both negative, then they will repel each other. However, if they're opposites, that is, one's a positive and one's a negative, they attract each other. So if Q1 is positive, Q2 is negative, that means Q1 is going to be pulled to the right towards Q2, and likewise Q2 will be pulled to the left towards Q1. So if I'm going to write down the force on 1 because of charge 2, I know that force has to be positive because the force is pulling Q1 towards Q2, and that means it's moving to the right. Whereas, if I wanted to calculate the force on 2 due to charge 1, well, I know this force has to be negative because Q2 is pulled to the left towards Q1, so the force is to the left. Okay? It's very important when you plug these numbers in, you always plug all positive numbers everywhere, and on the outside, you either make it positive or negative, depending on which direction the force should be. Okay? Another thing to remember is this 1 over 4 pi epsilon naught business. Sometimes you'll see it written as a K or a kappa. And what we're going to use as the number is just 9 times 10 to the 9. Okay? That's just a constant. Of course, in more complicated problems, which we will see later, if these charges are arranged in a medium that's not the vacuum, so maybe we have some kind of a conductor, and we put this conductor inside of maybe a gas or water or something, and we want to know how these charges will interact with each other while this item is in this medium, then we're not going to use this number. Rather, epsilon naught will become a different number, a different epsilon, and so 9 times 10 to the 9 will become some other constant. Okay? But for these problems, especially at the beginning when we're just learning this theory, we're just going to use 9 times 10 to the 9 every time. All right, so now what I want to do is let's do an example. Last time we did the example of two charges applying a force to each other, and we wanted to know what's the charge on one due to the other. Now we're going to do a much more complicated problem that really dives into the fact that these are vector equations we're talking about, and directionality is going to matter. Directionality, not just positive versus negative, moving to the left versus moving to the right, but also x and y components. Okay? So here's the problem. This is our coordinate system. This is the x direction. This is the y direction. Let's say we have three charges. Here they are aligned this way. So Q1, let's say it's 1 times 10 to the minus, let's make it minus 3. Let's see, this is Q2. I'll make it negative 2 times 10 to the minus 3. And I'll have Q3 is 3 times 10 to the minus 3. Okay? So three charges, there they all are. Some are positive, some are negative. Next, the distance from 1 to 2, I'll call that R12. I'll make that, let's say, 4 meters. And the distance over here, R13, I'll make it 3 meters. Okay? So there's our setup. We've got a system of three charges arranged in a certain way. And what I'd like to calculate is find the force on 2, the total force felt by 2, charge 2. Okay? That's our problem. What is the total electric force felt by charge 2 due to all the other stuff in the system? All right, so there's our situation. How do we want to go about doing this? Well, the answer is that the total force felt by charge 2 is going to come, thankfully, by a very, very powerful theorem or principle. And this is called the superposition principle. What the superposition principle says is, especially if things are nice and linear, then the total interaction between an object and its system, all the other things in its system, can be broken down into individual pieces, and then you add up all the individual interactions together, and that gives you the total interaction as a whole. Very similar. We've seen this in general physics all the time. You have, let's say, here's the situation. Here's the ground. We have a block, mass m, and we've got some set of forces, F1, F2, and I want to know what's the acceleration of this block. Well, we've got mg, we've got the normal force, and we've got two other forces. There's 4 forces sitting there if I don't even include friction. If I want to know the total force felt by this object, the way I did it in general physics was I said, hey, the total force is just the sum of each individual force independent added together. Which makes perfect sense. I would hope things work this way, generally speaking. And indeed, for electricity, thankfully, they do. If I've got 3 charges, then the charge on one of the 3, or the force on one of the 3 charges, is coming from two other charges. So Q2 is going to feel a charge from Q1, or force, I'm sorry, and a force from Q3. And so the total force he feels is the force from 1 plus the force from 3, just like in this particular illustration there. Now, we can't always do this in all of physics, because there will be times in very complex systems where superposition is not true anymore. That if you have a system that has 3 parts, then if it only had one of the parts, it would act a certain way. If it had a second of the parts by itself, it would act a certain way. Or a third, just a third part by itself, it would act a certain way. But if I put all 3 parts together, it's not the same as if I just added up each individual one. That violates superposition. However, for our purposes in this course, superposition principle will hold. That's a very good thing, because it means that the force felt by charge 2, the total force, is just the force felt by 2 due to 1 plus the force felt by 2 due to 3. Okay? Again, I'm putting these vector arrows on for now just to explicitly show you have to remember these are vectors. But, okay, so that's all we have to do. Well, what do I know? The force on 2 due to 1 is our k, the 1 over 4 pi epsilon naught, q2, q1 over r21 squared, plus force on 2 due to 3 is k, q2, q3 over r23 squared. Right? That's all I have to do. However, let's go back to thinking about this problem, visualizing it, trying to get it conceptually before I go plug numbers in. So let's think about, what does 2 feel? Forget about charge 3 for now. All that's here is charge 1 and charge 2. Okay, so just these 2 charges here. What do we know? Q1 is positive, Q2 is negative. They're going to attract. So the force felt by 2 is attractive towards 1. So that means Q2 will feel a force to the left. There's our F21. Okay? Now, pretend Q1 doesn't exist. Only 2 and 3 exist now. What do we know? Well, Q3 is positive, Q2 is negative, they're attractive. So the force felt by 2 due to 3, remember it's always in the line between, or along the line between the 2 charges. So Q2 will feel a force this way due to Q3. So that's our F23. All right. So if we plug our numbers in, we get these 2 vectors, F21 and F23. I have to add these 2 vectors together. And that'll give me my final answer. Very nice. However, we know there's an issue about adding vectors. And the issue is, if you have 2 vectors that you need to add together and they don't point in the same direction, then you can't just add them. You can't say, I walk 5 meters to the right and I walk 10 meters to the north, so 5 to the east, 10 to the north. I add them together, that means I walk 15 meters northeast. No, that's not true. The only vectors you can add directly are vectors that point in exactly the same direction. And obviously these 2 vectors won't be pointing in the same direction. One's straight to the left, the other one's at some weird angle. So we learned in general physics, the trick to being able to do this, even though technically we shouldn't be able to, is to break up each of these forces, F21 and F23, into X pieces and Y pieces. And then I could add the X piece of 2-1 to the X piece of 2-3 and get some answer. And I could add the Y piece of 2-1 plus the Y piece of 2-3 and get some answer. And then once I have those pieces, I can then do a little trigonometry to get what's the hypotenuse and what's the direction, what's the magnitude and direction of this thing. So technically, what I should be writing is F21 or the force F2 is going to have two pieces, the x piece and the y piece. The x piece of F2 is going to be the x piece of force 2-1 plus the x piece of force 2-3. And the same for the y's. The y piece of the force is going to be the y piece of 2-1 plus the y piece of 2-3. Okay, so that means this is what I want to do. Because once I have these, then I know the magnitude of F2 is going to be the square root of F2x squared plus F2y squared. And the direction of this force is given by the inverse tangent, F2y over F2x. Okay? That's what I want to do. Once I do all of this, I'll have my answer. So this question breaks down into these parts. I want to find the total force F2. That means I need its magnitude and its direction. In order to get its magnitude and direction, I need to get the x and y pieces of force 2. To get the x and y pieces of force 2, let's look at the x pieces. The x piece of force 2 is going to be the x piece of all the forces acting on 2. So he's going to feel a force from 1, and he's going to have an x piece of that, that's this part. And then he's going to feel a force due to 3, and he's going to have an x piece of that. I add all those pieces together, I get my total x piece. Likewise, he's going to feel a force from 1, y piece, and he's going to feel a force from 3, y piece. Add those y pieces together, that gives me a total y piece of my force. Okay? So, how do I get the x pieces and the y pieces of my little forces? That's where I start using these equations here. Okay, so let's see. Let's see it in action. Now that I have kind of my setup, I know what I'm going to go for. Let me redraw this. Here are my charges. 1, 2, and 3. The distances from here to here I have is 4. Here to here I have is 3. I believe that's what I did, right? Yeah. Okay. So let's start. We're going with the x stuff first. Okay. In the x direction, what do we have? The x piece of the total force on 2 is equal to the x piece of the force on 2 due to 1 plus the x piece of the force on 2 due to 3. Okay, so what's the x piece of the force on 2 due to 1? Well, first we write down what's the force on 2 due to 1, forget about the x, and then I stick something in to make it the x component. Okay, so the x piece of the force on 2, or what's the force on 2 due to 1? Well, I know it's 9 times 10 to the 9, that's the k, that's the kappa, times the charge, charge 2, let's look at what was 2, minus 2 times 10 to the minus 3. Again, we don't put the negatives in, so it's just 2 times 10 to the minus 3. And then charge 1 was 1 times 10 to the minus 3. Divided by the distance from 1 to 2, well, that total distance is 4, and that's squared. And then remember, I have to put in positives and negatives myself. So is 2 going to move to the right, or is it going to move to the left in the x direction? Because charge 2 is negative, charge 1 is positive, they attract. That means 2 will move towards 1, which means he's negative. Okay? In fact, let me go ahead and make sure that's not hidden. Now, what I've written is the total force on 2 due to 1, but I haven't made this the x component yet. Now I make it the x component, and usually what you do is cosine or sine or whatever. But notice, for this particular part, 1 and 2 are on this x horizontal axis. All of the force is in the x direction. There's no amount of this force which points in the y direction. So I don't have to put cosine or sine here. It's just like if I were doing, let me do this, it's just like if I had, here's a force of 100, and then I've got this force of 50 at an angle of 30 degrees. Okay, and I want to know the total force in the x direction. Well, the first force of 100, that's the force. He's moving to the right, so he's positive. And now I'd usually do cosine of theta or sine of theta to make it the x component. But notice the force is already in the x direction. So I don't do anything about that. But then when I go to the next piece, there's the 50. He's to the left, so he's negative. How much of this 50 is pointing in the x direction? Well, now I do my sines and cosines, and it turns out it's cosine 30, right? So if the force is already in the x direction, I don't have cosine or sine. If the force is at some weird angle, that's when I have to do cosines and sines, right? So here, that's exactly what I have here. The force on 2 due to 1 is straight to the left. So he's already in the x direction, so I don't need to put a cosine or a sine on him. I do have to remember the negative, he's moving to the left, but that's the x component. Next, plus, now I need, what's the force on 2 due to 3? This is a little bit more complicated, but let's go ahead and draw it on the picture. Force on 2 due to 3 goes this way, okay? Remember, 2 is a negative charge, 3 is a positive charge. They attract, so 2 is moving towards 3. What's his force? Well, it's 9 times 10 to the 9 times charge Q2, 2 times 10 to the minus 3, always positive, times charge 3, that's 3 times 10 to the minus 3, divided by the distance between them. Well, notice I'm not given the distance between 2 and 3. I'm given the distance between 1 and 2 and 1 and 3, but not between 2 and 3. So to get this R, R2, 3, I need to figure out what it is. Now, that's not a big deal. Notice what I have. I've got a right triangle. This is 4, this is 3. I need this distance. Well, how do I get that distance? That's just Pythagorean theorem. R squared is 3 squared plus 4 squared, which is 25. So R is just 5. Okay? So I now know R23 is 5. So that's a 5 squared. Okay? Next, I need to make this the x component only. Notice what I've written is the total force 2 feels from 3. But that force is at this weird angle right now. I don't want the angle, I only want the x component. So I've got two options. And let me explain this a little bit to the side. Here is my problem. This is 4, this is 3, this is 5. I've got a charge here and I've got a charge here. And my force is pointing that way. I want to know how much of this force is in the x direction. So either I could find this angle theta, and once I know this theta, then the force is going to be cosine theta. The x piece of the force is the total force, which I've already written, times cosine theta. So all I have to do is calculate what is this theta, and then I stick it into cosine theta, and I'll have my x component. But there's a second way of doing it. The other way of doing it is what's called similar triangles method. So if I've got this triangle drawn like this, where these are the distances, right? 3, 4, 5, those are the distances between these charges. And I also have the same triangle, where here's Q, and this is F, 2, 3, right? This force is F, 2, 3. And I only want the x piece. Well, these two triangles are the same triangle, but their sides have different lengths, right? F23 is not 5. 5 is the distance only. But I could draw a triangle for the distances, I could draw a triangle for the force, and they're similar triangles. And if you have similar triangles, it turns out that the ratio of sides of one of the triangles is the same as the ratio of sides of the other. So for this bottom triangle, if I call this F23Y and F23X, right, the X piece of force, the Y piece of force, and the total force, if these two triangles, first of all, the theta is the same theta because they're similar triangles, then it must be that let's say F23X divided by F23, so that is the ratio of the X side to the hypotenuse, is the same as the ratio of the X side to the hypotenuse of the other guy, 4/5. It's the same thing. And what that means is, instead of having to calculate what is theta and then write down cosine of theta, I could just write down this instead. And why? Why 4/5, not 3/5 or 3/4? Well, all I did here was I said, hey, if I wanted cosine of theta, what's cosine of theta? Cosine of theta is the side adjacent divided by the hypotenuse. Cosine theta is the adjacent side over the hypotenuse. And the adjacent side here is F23X over the hypotenuse, which is F23. And for this triangle up here, same thing. If I want cosine of theta for him, that's his adjacent side, the 4, over his hypotenuse, which is 5. And since they're similar triangles, this guy's cosine theta and this guy's cosine theta are the same thing. So instead of writing cosine theta right here, I could write 4/5, or this thing. They mean the same thing. They're all the same number. So this is the trick I'm going to do. Because I already know the ratio of sides, why go through the trouble of calculating an angle and then using trig on the angle? Just use the ratio of the sides from the beginning. You have to do one less step. And if you've taken statics with me, that's what a lot of engineers do. When they're doing statics, they're trying to do truss analysis and things like this. Usually, they're not given angles in the problems. They're given how long are the beams. And so they take the ratio of the lengths of the beams instead of doing cosines and sines, because you get the same answer. So here, our actual problem, notice what I want. What I need to do for this red vector, remember I've just calculated what is this force. That's what this stuff right here is. But that force is at this angle, and I only want the x piece of this force. So that means I'm going to do cosine theta, but I don't know theta yet. So either I could go through the trouble of calculating what is theta, 36 degrees or whatever. And then once I know this 36 degrees, now I do cosine of that number. Well, instead of going through that trouble, let me just use the ratio of the sides. Cosine theta is adjacent over hypotenuse, or x side over total distance. And I know for our triangle here, 3, 4, 5 triangle, the x distance is 4, the hypotenuse distance is 5. So this thing I just wrote right there is the same as cosine theta. It's the exact same number. So all I did was write F2 cosine theta. But instead of writing cosine theta, I did the actual ratio of the sides to get the answer. Okay, I'm not done yet. One more thing we can't forget is directionality. Is this to the right or is this to the left? Well, I showed it on the picture already, but just from our intuition, charge 3 is positive, charge 2 is negative. They attract, which means 2 is going to move towards 3. And in the x direction, that means he has to move to the left. To the left means negative. Okay, and there we go. Now, every single force felt by charge 2 is written down on my problem here. Only x components. And so now I could calculate this stuff out and get an x piece. So what do I have? I've got All right, 1 times 10 to the minus 3 divided by 16 plus 3 times 10 to the minus 3 right, and I believe this comes out to be minus 5103. Okay, negative to the left, and it's this amount. This is only the x component of the force felt by charge 2. Now, we want to do the same for the y component. Okay. Well, in the y direction, what do we have? Well, F2y, just like before, is F21y plus F23y. Okay. So F21y. Well, I could go ahead and start writing down just like I did before, 9 times 10 to the 9 times 2 times 10 to the minus 3, blah, blah, blah. However, a little intuition goes a long way here. Notice, charge 1 and charge 2 are directly in line on the x-axis. That means the force that 2 is going to feel from 1 is purely in the x direction. He's got no y component. So I know automatically the y piece of F21 is just 0. I don't even have to calculate it. Now, if I wanted to, I could. I'd write exactly what I wrote right here, and then I'd have to put cosine or sine. In fact, I'd have to put sine of 0. The angle between 1 and 2 is 0 degrees. I want the y component, that's the sine. Sine of 0 is 0. So again, I'd get a 0. But instead of going through the trouble of writing something I know is already 0, I'll just write it down as 0. There it is. If you're not sure, write down the calculation. Let it give you 0. That's fine. Now, F23, we're not as lucky. Let's look at F23. F23, the force on 2 due to 3. That's 9 times 10 to the 9 plus 2 times 10 to the minus 3 times 3 times 10 to the minus 3 divided by the distance between them. We already calculated that to be 5, so that's 5 squared. This is the total force felt by 2 due to 3, but I only want the y component. So usually I'd write sine theta here. However, I don't know theta, and just like I did before, cosine theta is the same as the x side, the x distance divided by the total distance. The y component, sine theta, is going to be the y distance over the total distance. So for sine theta, I'm just going to write 3 over 5. Okay? Now remember, 4 over 5, 3 over 5, that's how you get cosine theta and sine theta for these distances. If I have some other problem where the distances are not 3, 4, and 5 anymore, then I have to use those numbers instead. So don't just memorize cosine of theta is 4 over 5. That's only true if the distances are the same as we're dealing with in this problem. But these are the distances here, so the y part, sine theta, is the y side over the hypotenuse, which is 3 over 5. One more piece, is this positive or negative? Well, 2 is attracted towards 3, which means it wants to move up and to the left. In the y direction, up is positive. So this is just positive. All right. So now we calculate this stuff out, and let's see what we're going to get. First of all, we know it's positive, and get, I believe, 1296 newtons. Okay. So there we go. I now have the y component of the total force felt by charge 2, and I have the x component of the total force felt by charge 2. But that's not my answer yet. Remember, I want the total force felt by this charge. So now, let me go ahead and erase this stuff. All right, and we get, what were these numbers? So 5103. So F2x is minus 5103, and F2y is positive 1296. So that's what we found before. Now I want to get my final answer, which is what's the magnitude and direction of this total force. Magnitude F2 is the square root of F2x squared plus F2y squared, which is, in the parentheses, minus 5103 squared plus 1296 squared. All right, so that squared plus 5103 squared, square rooted, gives me a total force of 5265 newtons. So that's my magnitude. That's how much force is there. But I also want to know what's the direction. The direction, inverse tangent of F2y over F2x. That's the inverse tangent of 1296 over minus 5103. So 1296 divided by minus 5103, inverse tangent, gives me minus 14.25. Now, degrees. Now, before I accept this one, remember what we learned back in general physics with these vectors is half the time you find this angle, it's going to be wrong. And it's going to be wrong because there's an ambiguity as to this negative 5103 is the negative to your calculator in the top, the numerator, or the denominator. It can't tell. Obviously, we know it means two different things. If negative's in the denominator, that means the x piece is to the left and the y piece is up. If it's the other way around, if the negative's in the numerator, that means the x piece is to the right and the y piece is down. That's two completely different directions. Only one of them is the right one for our problem, so we have to be careful about this. So before I box this answer, let me go back and think about what it should be, right? What should the answer look like? Well, if I've got this charge 2, and it's being attracted towards 1 and attracted towards 3, I know for sure it's moving to the left in some way. And I know it has to be moving up towards 3. So for this particular problem, I can visualize what I should be getting. I should be getting a total force that's up and to the left. Okay? The other way to think about it is to look at these two x and y components. I have a total x component here, which is negative, and a y component, which is positive. So I know the final answer should be to the left and up. So again, up and to the left. This answer I'm getting, negative 14.25, if I were to draw that, that's somewhere down here. That's down and to the right. That's the wrong angle. So because I know it's the wrong angle, I know immediately all I have to do is add 180 to this, and that'll give me the right angle. So the actual answer is 165.75 degrees. And there we go. Given the problem, here it is, 3 charges aligned in a very peculiar way, distance apart in some ways, and you want to know what's the total force felt by one of these charges. In this case, it happened to be find the force on 2. How did we go about doing it? Well, I kind of went backwards. I thought about what would the answer look like. I need a magnitude and direction, because these are vectors. In order to get magnitude and direction, I need the x and y components of my force. Okay, well, to get the x component of my force, all I have to do is get the x components of each individual force and add all those things together. Likewise, to get the y force, I get the y component of each individual force separately and I add all those together. How do I calculate these things? I use the Coulomb force equation. K Q1 Q2 over R squared. For each one of them, of course, I'm going to have x and y component stuff to worry about, plus and minuses to worry about. But you keep track of it all, calculate it out, you get your 2 x and y components. Once you have those, then you do magnitude and direction. Being careful when you do direction that the answer you get, do you have to add 180 or not? In this case, I had to, but there's going to be other times where you don't have to. So don't always add 180. It's just that for this problem, I had to because the answer it gave me was wrong. Right? That's how you're going to go about doing these problems. How can things change? I could just arrange the charges in different ways, right? I could have 3 charges like this. I could do a square, 4 charges. And I want to know what's the force here. I could have a system that's like this. I've got a charge here and a charge here. Q1, Q2. Maybe this is positive and this is positive. And I want to know where should I put Q3 such that the net force on Q3 is 0. That sounds like a different type of problem, but really, let's say it goes here. All you have to do is say for the force on 3 better be equal to 0, and that is the force on 3 due to 1 plus the force on 3 due to 2. So if I don't know where to put Q3 yet, I'm going to have to tell you where it is. That means I don't know the distances, but I'm going to guess. I'm going to say, okay, let this distance from here to here be x, and then from here to here be the rest of the way. So maybe, from 1 to 2 is 10 meters. So then if from 1 to 3 is x, that means from 3 to 2 must be 10 minus x. So I'm going to have k q1 q3 over 1 3, which is x squared, plus k q3 q2 over 10 minus x squared. And then if Q3, let's say Q3 is a negative charge, well, that tells me Q3 will try to move to the left for 1 and try to move to the right for 2. Set these equal to 0 because I want the net force equal to 0, and then I solve for whatever x is. Okay? But it's the same problem. You have multiple charges in your system. You look at each charge individually, separately, and add up all the effects. So 3 will feel an effect due to 1. I call that F31. And then 3 will feel an effect due to 2. That's F32. I add those 2 effects together. That gives me a total effect. In this particular question I posed, the effect is there's no net force. So calculate what is x. Okay? So I can give all sorts of different styles of questions, but at the end of the day, they all lead to the same basic mechanics. You know the equation. You know you have to put in when is the force positive versus negative. You have to calculate distances sometimes if they're not given. You have to worry about x and y components if we're at different angles. But if you keep track of all that stuff, the calculations really aren't that bad. It just looks kind of messy. Lots of numbers, lots of scientific notation stuff, but the physics of it's pretty easy. Now what we're going to do next time is show when does it get not easy anymore. So that is to say, let's say we have the system and maybe there is a sphere of charge and then some charge Q1 here. And this sphere has a total charge of Q. That sphere is made up of multiple charges, maybe 1 million charges, maybe 1 billion charges. I don't know how many charges are in this sphere, but they're all going to contribute some amount of force. So I'd have force Q to here, Q to here, Q to here, Q to here, all sorts of forces. Each one, I have to do F is K, Q1, Q whatever, over R1 whatever squared. I need 1 for every single charge that's in the sphere, and then I add them all together. Each one is at slightly different angles, so I have x and y components for everything. This is a very, very complicated question if I don't have a trick to get around it. And that's what we're going to talk about next time, and that is Gauss's law. Gauss's law is going to make very complicated questions like this, if we had to do it this way, the Coulomb law way, it would make it very easy. If we try to do it with just pure Coulomb's law and vectors, you're going to be here for 1 billion years. Computers would not be able to handle the number of calculations necessary. But you're going to be able to do it in 2 or 3 lines. Really easy. So that's what we're going to talk about next time, Gauss's law and the electric field. Okay, so that's what you can look forward to. For now, I hope this was helpful. Definitely practice examples, practice the problems posted, because even if it kind of looks simplistic, even if it makes total sense as you're watching, it's not until you sit down with your blank sheet of paper and you need to do it yourself that you realize where you have questions, where little things might pop up and say, oh, I didn't think about that. Okay? So practice a lot. Once you practice, you get very used to this, and it's just a matter of not making stupid little mistakes about signs, positives and negatives, or when do I do cosine theta versus sine theta, all that kind of stuff. Okay? Anyway, until next time, I'll see you later.